Indian Statistical Institute. His research interests are in quantum error correction and near-term quantum computing. He did his BSc in Physics and post-BSc BTech and MTech in Computer Science from University of Calcutta. He is a gold medalist from the university and received the prestigious EST Inspire Scholarship. He was also a long-term intern at the Quantum Computing Group, IBM T.J. Watson Research Center, with the coveted Fulbright Nehru Doctoral Research Fellowship. He is also a Qiskit advocate. So, Ritajit, we can proceed now.
Yeah, thanks for the introduction, Debashmita. So, so this talk is on introduction to quantum computing, and we will try to go over the very basics of quantum computing, mainly the postulates, and I hope that everyone will gain something from this, even if you know these basics. So is my screen shared? Is it visible?
Yes, it is visible.
Okay. So, so let's start with this session. As I said, it's the introduction to quantum computing, and I am was uh, declared for Deutsch, Shore, Bennett, and Brassard, and I am sure you will hear all of their names throughout this Qiskit Fall Fest. So what I can expect that during your algorithm course, you will hear about Deutsch and Peter Shore, and tomorrow for most likely there will be super dense coding, which is one of Bennett and Brassard's one of the awesome works by Bennett and Brassard. So we hope that someday maybe some of you can also go ahead and get something like this done in this field. But before you actually maybe start preparing your speech for these, we should know what the basics of quantum computation is. So we'll start with, these are the agendas for today. We will start with qubits, which is the building blocks of quantum computers, and then how we can evolve these qubits and how we measure this qubit, what happens when we have more than one qubits, and finally one very important theorem called no cloning theorem. So let's start with this. We will start with qubits. So qubits, as you can understand, they are named like a analog of classical bits. In classical computers, we have bits, zeros and ones, and qubits, quantum bits, they are named like this analog of that. So one important thing here is there is no good classical analogy of quantum mechanics. So whatever we try to visualize, understand with examples, they can go as far as possible, but never perfect, because quantum is quantum and nothing classical can actually properly say what it is doing. But here is one example that we can try to understand what happens that why is quantum computer supposed to be so powerful? Like it's a hype that Shor's algorithm can break this RSA crypto system and all of those things. So why is quantum computing so powerful? So let's suppose that we have two tasks that we want to do, task A and task B, and you will give me a coin and I will do only one task at a time. If you give me the head side of the coin, I'll do task A, and if you give me the tail side of the coin, I'll do task B. So if you want me to do both the tasks, you will have to give me two coins, obviously. But what happens if you can somehow place the coin on its edge, like this picture? If you can do it, then maybe you can argue, well, this is in some sense both head and tail together. So now I am giving you coin on the edge. You have to do both task A and task B. So this is perhaps a good, not maybe as good as it can get, analogy of what a quantum bit does. We will see in the next slide more rigorously. But so now using just one coin, you have been able to perform two tasks, whereas you would have needed two coins beforehand. What if you have two coins on the edge? So now you can do actually four tasks. So two tasks for the first coin, two tasks for the second coin, four tasks. On the other hand, if you were doing this with either heads or tails, you would have needed four coins. Similarly, you have three coins, you have eight tasks. So you understand this is growing exponentially. So if you have n such coins on the edge, you can, sorry, so if you have n such coins on the edge, you can do 2 to the power n tasks with n coins. So this is something that gives exponential speed up to quantum computation. So now let's move to something that is actually more quantum than this coin analogy. And let's try to think of light. So light here has something called polarization. So the light can vibrate along this axis. As you see the horizontal polarization, it is perhaps vibrating on the plane of the axis, or the vertical polarization, it is perpendicular to the plane. Now these two things are perpendicular to each other, as I said. So you can say in analogy of classical computing that if it is like this, then I'll call this 0. If it is like this, I'll call this 1. So what is this funny notation I just wrote? I'll explain to this. What is this angular bracket thing? So instead of saying that, yeah, this is horizontal polarization, vertical polarization, all of those things, I'll just call this as 0 and this as 1. This is called the Ket notation. So Ket 0, Ket 1. So here is one more example. Suppose you have an electron with spin up or spin down. So instead of calling it spin up, we will just again call it 0. Instead of calling it spin down, we will again call it 1. So for the rest of this entire call fest, and if you continue with quantum computation and you are not too much into the exact experimentation, for your entire quantum computation life, we will not really bother about whether it is a polarization, whether it is electron spin, or whether it is Josephson junction, whatever it is, we will just give it some abstract mathematical notation and we will call it 0 or 1 in analogy to classical computer. But in terms of mathematics, these are vectors. So the 0 is written like this, 1 and 0, and 1 is written like this, 0 and 1. So always we will consider this type of zeros and one, and we won't worry about what it is inside. We are just happy with this abstract mathematical notation. So now who said that the electron spin maybe needs to be spin up or spin down? What if it is like angled in this way? So one more thing that you can check, this Ket 0, this is something called bra 0. This is nothing but the row notation with complex conjugate, but there are no complex numbers, so it is just a row. So if you just see, this is called inner product of 0 and 1. What happens? This is 1, 0, this is 0, 1. And if you do this calculation, 1 times 0 is 0, 0 times 1 is 0, that is 0. So these two are called orthogonal. So if this inner product is 0, mathematically speaking, we will call this orthogonal. We already said that this is horizontal polarization, this is on the plane, and vertical polarization is going orthogonal to this. So our mathematical notation is fine with this. So who said, as I said, that who said that the electron cannot maybe have a slightly angled notation? So how do we represent this? So suppose we say this is the axis and this would have been the 0 and this is orthogonal. So we can draw an orthogonal axis like this. This will be 1. So if this is the angle between these two, this is just a vector. So we can write this as cos theta 0 plus sin theta 1. Or if you are not really interested in, oh, wow, how come you got this cos theta, how come you got this sin theta, we can simply call this as some alpha 0 plus beta 1. So it is some way in between 0 and 1, and how close it is to the 0, that is defined by alpha, how close it is to 1, that is defined by beta. So this is what we will call as superposition. This is something very special. Superposition, this is something very special to quantum. It has no classical analog, although I gave you a coin example, but you can think of it like coin on the edge. So it is both 0 and 1 at the same time in some way. Similarly, you can represent this as, so this you can think of like maybe 0 here, 1 here kind of thing. So it will be some sort of alpha 0 minus beta 1. So we have something called superposition here. Let's dive even a bit deeper, because it is some way better to get a little understanding of the mathematics so that we can grasp our examples that we are learning better. So as you perhaps know, even if you don't, that there is something called a Schrodinger equation which governs quantum mechanics. So psi is some quantum state, for our case qubit, and this equation basically governs how psi evolves over time. So this h bar is called something called Hamiltonian. We are not going to worry about this, what this Hamiltonian is for this, but you can just know that this is a Hermitian operator. So if you recall what a Hermitian operator is, it means basically that this dagger is equal to this. This is a matrix. This dagger is equal to this. So Hamiltonian in one way encodes the total energy of the system, but as I said, we are not going to worry about this. You can check from this equation, why this equation I brought this up, that if say psi1 is some solution to the Schrodinger equation and psi2 is some other solution, then some alpha psi1 plus beta psi2 is also a solution. So in our previous example, we took psi1 as 0 and psi2 as 1, and we said that alpha 0 plus beta 1 is also a qubit. This is also a qubit. So this is quantum superposition. And this picture that you see below, this is something called Bloch sphere. I won't go deep into this today. You will learn about a bit of Bloch sphere tomorrow. But for the time being, you can think of like Bloch sphere as a good visualization of the quantum state. And here, as you see that if the vector is pointed upward, it is 0. If the vector is pointed downward, this is 1. See the third figure, the vector is exactly halfway between 0 and 1. So this is what we will call as equal superposition. So it is halfway, so it is equally likely to be 0 or equally likely to be 1, or in other way, it is equidistant from 0 and 1. On the other hand, a superposition need not always be equal superposition. It need not be equidistant from 0 and 1. This fourth picture, as you see, it is more inclined towards 0 and less inclined towards 1. So any point on this sphere, on the surface of this sphere, is a valid quantum state. On the other hand, if you are doing only a classical computer, only these first two figures, they are valid classical bits, zeros and ones. So that's all about quantum superposition I wanted to talk about. But okay, so we have quantum bits. Now, if we want to do something very useful with it, we need to evolve it. So think of classical systems. We have bits, zeros and ones. What do we do with it? We operate some gates on it, AND gate, NOR gate, NAND gate, so many gates. So we will see what such quantum gates are, how these quantum systems evolve. So again, we will take a dip into this Schrodinger equation. This was the Schrodinger equation. How can we solve it? It is not difficult if you see. We can simply write this as IH bar d psi, taking psi below here, is equal to H dt. So again, d psi over psi is equal to minus I over H cut H dt. So what happened here? The I would have gone to the denominator, and I can take it to the numerator by making it minus I, right? So if I integrate both sides, so these portions are constants. The integration will be just over this. What will happen? What is the integration of d psi by psi? It will be log psi, ln psi, logarithm, natural logarithm. So ln psi is equal to minus I over h bar h times t. There should be an integration constant which I am skipping for the time being, deliberately skipping for the time being. Why I am skipping, that will be like properly understandable in a few slides. Why it, what this particular constant does here. Now, what is then this psi? If log of psi is this, then psi is basically e to the power this. So what? Oh, I'm so sorry. So what we can say here, just we did this calculation here. If you recall that this I h cut t psi over psi is equal to h dt,
Ritajit, are you
and
sharing your screen?
yeah, is it not shared?
I can't. I can't see it. I don't know about others.
Oh, just give me a second then,
Can you
please.
please write in chat if the screen is visible or not? No, the students can't see the screen.
Just give me a second. Sorry.
And one thing I would like to announce that the attendance form is already given in the chat, so please fill that.
Visible now?
Yes, it is loading. Yes, now it is visible.
Okay, great. Yes. So we were doing this calculation, and what we showed here is simply this. And if you just missed it, it's like d psi over psi is equal to minus I over h bar h dt. And if we integrate this simply becomes natural log of psi is equal to minus I h cut h t. And from there we get that if I start at time 0 here, and if I use this operator on this state psi at 0, then we get the state psi at time t. So this is how we have evolved the qubit. So this is something we can call as a quantum gate. So this is a quantum gate which is evolving the qubit from this time 0 to time t. How this will be evolved will depend on the Hamiltonian and on the time, obviously, but we won't worry about that right now. So what is the property of this quantum gate? If you look into it closely, if we take the dagger of it, what is dagger? It is conjugate transpose. So transpose, what we did just a few minutes back, like you take the column vector to a row vector, and conjugate means plus I becomes minus I becomes plus I. And as I already said, this Hamiltonian H is a Hermitian operator, which means H dagger is equal to H. So if you take the dagger, H doesn't change, minus I becomes plus I. Now, if you actually operate this, if you multiply this operator with its dagger, this becomes identity. So that is the property of a unitary matrix. Therefore, our Schrodinger equation here dictates that you can have any quantum gate, just like you have so many classical gates, you can have any quantum gate, any matrix. This is anyway a matrix. Any matrix is a quantum gate as long as it is unitary. So this is what we can say about quantum gates mathematically. Now let's see some examples, some concrete examples. So this is what is called an X gate. As I said, it's a matrix, and we won't really bother in this course how it is coming from the Hamiltonian or some things like that. But how does it work? So if you remember what was zero, so here we have this X gate, zero was 1 0. So if you do this calculation, this will become 0 1, which is 1. You can do this calculation. So it's 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0. So it's 0 1. Similarly, if you do this on 1, 1 was 0 1. This was the 1 vector, and this will become 0. So this is like a quantum analog of NOT gate. So you can think of it as a quantum NOT gate. What does a classical NOT gate do? In classical system, we have a NOT gate which is denoted like this. It takes 0 to 1. So there is no gate there in classical. It takes 0 to 1 and 1 to 0. So it is also taking 0 to 1 and 1 to 0. So it is a quantum analog of NOT gate. Similarly, you can have something called, these are called Pauli gates, Z gate, Y gate. We will see Z gate a few slides later. But let's come to something called this Hadamard gate. So just recall, this is Hadamard gate. This is a gate, and what we were seeing previously, the uh, hat on the top of H, that was a Hamiltonian. That is something different. This is just a gate. So let's do this calculation. So we have 1 1, 1 minus 1. This acting on this state 0. What happens? The 1 over root 2 is there. So if you do the first calculation, the first row becomes 1, the second row also becomes 1. Now we can write this as 1 over square root 2, 1 0 plus 0 1, which means what is 1 0? That is 0. What is 0 1? It is 1. So now we have superposition. This X gate was not doing any superposition for us, but now we have a superposition. This is an equal superposition, as we showed. We will see again about this, that this is halfway between 0 and 1. And similarly, if you do the same calculation on, so this state is called plus. This is a very important state again for quantum computation. And similarly, if you do this calculation on the state 1, what you will get is 1 minus 1, which implies 1 over square root 2, 1 0 minus 0 1, which is 1 over square root 2, 0 minus 1, and this state is called minus. So you can again check what happens if we take the inner product of plus and minus. So let's try to see. So 1 over square root 2, 1 over square root 2 goes out as 1. And then we have 0 plus 1 times 0 minus 1. So let's open this up. We have half here. Then we have this 0 0 plus 1 0 minus 0 1 minus 1 1. So if you recall, I already said that 0 and 1, they are orthogonal, and we showed that if you take the inner product of 0 and 1, this will become 0. You can check that if you take the inner product of 0 and 0 or 1 and 1. So let's try, this is 0 and 0. This will be 1. So what we have is inner product of 0 and 0 giving 1, this giving 0, this giving 0, this giving 1. So this is 0. So that means plus and minus are again orthogonal. And what we won't go into because it will take up too much time if I go to that much details. But uh, if you draw something like this, maybe this is 0 and this is 1, they were orthogonal, you can verify that what this Hadamard gate does is that this is plus and this is minus. They are still orthogonal, but makes a degree of 45-degree angle with 0. So 1 over root 2 comes from cos 45. Okay, so these were two examples of quantum gates, specific examples that we have seen, and how it can, this Hadamard gate was creating superposition, X gate was not creating superposition, and you can prepare any unitary matrix like this, and that is a valid quantum gate. Now, when we are dealing with some quantum algorithms, mainly quantum machine learning type algorithms, what we need to do is that we need to tune parameters like you have in classical neural networks where you tune the weights over the edges. Similarly, here you tune the parameters. So you can have this parameterized quantum gates. So for example, this Rx theta. So this is rotation along the axis of X by an angle theta. So whatever value you put to this angle theta, that by that value, this gate will change. That is why it is called parameterized gates, because it is parameterized by the value of theta. You fix the value of theta and the gate will act accordingly. So if you start on the qubit 0 and if you start increasing the value of theta, this is how it will change. So it will start rotating from 0 and here to 1. If you still increase the value of theta, it will go from this 1 along this direction to 0. So this is rotation along the x-axis. So this was the x-axis, as you see. It is rotation along that. Similarly, you can have rotation along the y-axis. So this is the y-axis, as you can see here. This is the y-axis. Or you can have rotation along the z-axis. So this is the z-axis. These are parameterized quantum gates. Now, all of these are single qubit gates. They act on one qubit. So although we haven't still learned what happens when we have more than one qubits, we will just look into a two qubit gate. That is one of the most important gates that you will come across. That is called this C0 gate or controlled NOT. So this is basically this plus sign here is the NOT sign. X gate was the quantum NOT gate. And here we have what is called a controlled NOT gate. So this particular qubit is called the control, and this particular qubit is called the target. So the point of this is, if the control qubit is 0, then nothing happens to the target qubit. Whatever the value of target it goes unchanged. But if the control is 1, then the target is changed from 0 to 1 or 1 to 0. So if you look into this, when the control is 0, the target remains as it is 0 0 1 1. But when the control is 1, when the target is 0, it becomes 1. When the target is 1, it becomes 0. And obviously it also has this type of matrix notation. How can you find out the matrix notation from this type of table? It is actually pretty easy. You can write something like this. So we know that this is two qubits, both of them can be 0, both of them can be 1. We will come to what this means, but for the time being, imagine that we have two qubits, both of them are 0. The first one is 0, second one is 1. The first one is 1, second one is 0, and the first one is 1, second one is also 1. And similarly, this is the outcome that can happen. 1 0 and 1 1. So let's see what this thing is doing. When both of them are 0 and 0, what is the outcome? It is 0 and 0. So this portion becomes 1, nothing else happens. When this is 0 and 1, the outcome is again 0 and 1, nothing else happens. Sorry. So this is 0 0 0 1 1 0 and 1 1. This is 0 0 0 1 1 0 1 1. So this was 1, this was 1, Now come to 1 0. When the input is 1 and 0, what is the output? 1 and 1. So this portion becomes 1. And when the input is 1 and 0, the output becomes, sorry, in the input is 1 and 1, the output becomes 1 and 0. So everything else is 0. So we have the quantum gate. So if you can write down the action of the gate on the system, you can always write down its matrix in this form. Okay. So is there any questions, Debasmita, till now?
There is one question from Ayon Bhomi. Time
Mhm.
evolution operator is a quantum gate in all the three pictures, that is Heisenberg, Schrodinger, and Dirac. Is time evolution operator is the quantum gate in all the three cases?
So for this, we are sticking to the Heisenberg, to the, sorry, to the Dirac thing, not the Heisenberg, because in the Heisenberg, the idea is that the state doesn't evolve, but the operator evolves in itself. We are not going into that. We are considering that the operator is fixed in the time. Uh, in any time you fix the operator and the state evolves as it is. So that's the picture that we shall deal with.
And one more thing is, Anisha asked to repeat the matrix formation process again. I think
Oh,
of
yeah,
the C
sure.
naught.
Yeah, sure, sure. So let's do the calculation once more. So we have what happens. You can have, so you have two qubits. The qubits can be 0, 0, 0, 1, 1, 0, 1, 1. So let's say that the rows are the inputs and the outputs can be also 0, 0, 0, 1, 1, 0, 1, 1. So the columns are the outputs. So what we will try to see that when the input is 0, 0, what happens to the output? So when the input is 0, 0, the output is also 0, 0. So we will put a 1 here and nothing happens to the others. So 0. When the input is 0, 1, the output is 0, 1. So it's 1 here, nothing happens to the others. But when the input is 1, 0, the output is 1, 1. So here we have a 1, nothing happens to the others. And similarly, when the input is 1, 1, the output is 1, 0. So we get the matrix. You can try this out for the Hadamard gate because there is something, there is the idea of superposition, that the input 0 goes 50% to 0 and 50% to 1 and try to form the matrix of Hadamard gate. Just try it out and let me know in Discord if you are having problems. Okay. So let's move on to this third thing. When we think of classical computing, we don't really bother much about, or we don't even consider that there is something called measurement. We just take it for granted. So we just have bits and we have gates and we just know the outcome. It's either 0 or 1, something. But here, measurement is extremely important because the outcome can be a superposition. So what happens in the measurement? So this is perhaps the weirdest part of quantum mechanics. So all what we did beforehand, nothing was really very weird. So we had very discrete thing of what is called a quantum state. It's a vector. How do you evolve it? You apply a unitary matrix. There was nothing very like disturbing or anything about quantum mechanics there. But the disturbing thing comes now. So suppose we have a quantum circuit like this. How to build it? Debosmita will show you in few minutes. So we have this Hadamard gate acting on the qubit, and in all the quantum computers that we have now, the qubit always starts at 0. The qubit always starts at state 0. So we have this Hadamard gate acting on the state 0, which we calculated was giving 1 over root 2, 0 plus 1. So up to this point, here we have this particular state, 1 over root 2, 0 plus 1. Now the point is, whenever we say that we are going to measure, so this meter box, this means measure. So whenever we are measuring, it is always associated with some basis. So what basis? If not stated anything else, we always think that it is the Z basis. So what is the Z gate? This is the Z gate. This is also called phase flip because you can check that Z acting on 0 gives 0. It does nothing, but Z acting on 1 gives -1. So it is adding a phase of minus 1 on this quantum state ket1. So that is why it is called a phase flip gate. Now, if you find out the eigenvalues and eigenvectors of this particular Z operator, the eigenvalue plus 1, the eigenvector is 0, and the eigenvalue minus 1, the eigenvector is 1. So whenever we say Z basis, these terms go interchangeably. Z basis means 0, 1 basis. So whether I say it is Z basis or I say it's 0, 1 basis, they mean the same thing. That means you can either say it's the operator name or its eigenvectors. And we have already seen these relationships before. This is called the orthonormality relationship. Although we haven't yet seen normalization, we will see in a slide or two. So measurement means a basis. That's all. Measurement means a basis. But what happens with the basis? Well, the point is that once you measure in the Z state, it collapses to one of the bases, one of the eigenstates. So here comes the weirdness of quantum mechanics, I would say, that once you measure the superposition state, it will collapse to one of the eigenstates. So which eigenstate, 0 or 1? And how do you know whether you will get the outcome 0 or 1? So that is given by something called this Born rule. So suppose you have the state psi and you measure it in some basis b, then the probability of getting this outcome b is given by this. So don't get scared. We will do the exact calculation right now. So here we had again that we have this state psi was basically 1 over root 2 0 plus 1 over root 2 1, and we were measuring it in the z basis, which we said is equivalent to saying 0 and 1. So what is the probability of getting outcome 0? The Born rule says it is 0 psi square, mod of this square. So now let's see. 0, what is this? This is 1 over root 2 0 plus 1 over root 2 1 modulo square. So I can just take half out, and this is 0 0 plus 0 1 mod square. Now we have already seen that 0, the inner product of 0 with 0 is 1, and the inner product of 0 with 1 is 0. So we have this probability half. And if we write this, we also get 1 psi. The same calculation, if you see, I can take half out, it will be 0 0 minus 0 1 mod square. It's also half. So if you measure this particular state in the z basis, the z basis is also called computational basis because of the 0 and 1. Computations are done over 0 and 1. So z basis is also called this computational basis, and if you measure it in the computational basis, then you get 0 with probability half, you get 1 with probability half. So here comes the importance of measurement. Once you measure the state, you can have like superpositions or anything, but once you measure, all you have is either 0 or 1 with some probability, and the probability is governed by Born rule. So we will see one more example. Let's take a most generalized state. We have this alpha 0 plus beta 1. So what is the probability of getting this outcome 0 if we measure again in this 0, 1 basis? So if you see, we have alpha times 0, 0 plus beta times 0, 1 mod square. So this is mod alpha. 0 0 is 0 1, and 0 1 inner product is 0, so we are left with mod alpha square. And similarly, this is alpha times 1 0 inner product plus beta times 1 1, and this portion, the first portion inner product is 0, the second portion is 1, so we are left with mod beta square. Now we know that the probability should always add up to 1. So therefore, we have this condition that we didn't say before when we defined a qubit. We said it must be a vector, but it must be a vector such that mod alpha square plus mod beta square is always equal to 1. So this is called the normalization condition. So a qubit is a vector in a vector space. It is a unit vector because its norm is 1. Or in other words, if you square the coefficients, if you take the modulo square of the coefficients and add them, they becomes unity because of this requirement that the probability should sum up 1. Good. So we have already learned a lot. But as I said, that measurement is associated with a basis, and we talked about z basis. What happens if we measure in some other basis, say the x basis? So again, as I said, that whenever I say a matrix as a basis, it means its eigenvectors. So x gate we already have seen. This is the x gate. And if you find out its eigenvalues and eigenvectors, then the eigenvalues are again +1 and -1. The eigenvectors are exactly this. And we have seen that this eigenvector is what is called the plus state and the minus state. And how did we get the plus state and the minus state? Initially, by applying h on 0, we were getting plus. By applying h on 1, we were getting minus. Now, don't get confused here that how come h on 0 is giving plus and then you are saying x is giving plus. No, h is a gate that is operating on 0 and giving the state plus, whereas x is a measurement operator. When you measure the state, it will collapse to either the state plus or the state minus, because plus and minus are the eigenstates of this x operator. So here is a difference between measurement and evolution. What we showed before, this portion here is the evolution. What we are talking here is the measurement. So what is the probability of this? If we write down the probability of this, again, half comes out. We have alpha times 0, 0 plus alpha times 0, 1 plus beta times 1, 0 plus beta times 1, 1 mod square, and that's squared. And what we have already seen, so this is, we were taken half out. We had alpha times 0, 0 plus alpha times 0, 1 plus beta times 1, 0 plus beta times 1, 1 mod square. So again, this 0, 1, these are giving inner product of 0. So we are left with half mod alpha plus beta whole square. Similarly, if you do the calculation here, you will find something like half mod alpha minus beta whole square, if I am not wrong. So this will be like minus, this will be alpha times 0, 0 minus alpha times 0, 1 plus beta times 1, 0 minus beta times 1, 1. Yeah. So you get a different probability if you measure in a different basis. We measured this particular state in the z basis, and we had the probability of getting 0 as mod alpha square and getting 1 as mod beta square. But whereas if we measure it in x basis, we have this particular probability. So how you measure dictates on which basis you measure, dictates the probability and the measurement outcome. So here the measurement outcome is also different. You get the state plus with this probability, state minus with this probability. So the point here is that Qiskit or any other quantum computer, Qiskit is not a quantum computer, it's a programming language, but any quantum computer today does not allow measurement in any basis other than Z basis. So how can you deal with that? So suppose you have this quantum circuit here, X gate acting on 0. Remember that everything starts from 0. X gate acting on 0 gives 1. And if you are measuring this in the x basis, remember plus is, again, remember plus is 1 over root 2, 0 plus 1. So if we take the modulo square, we can take half out. So it will be mod of 0, 1 plus 1, 1 and this will be half because inner product of 0 and 1 is 0, 1 and 1 is 1. Similarly, this will be half out, it will be mod of 0 1 minus 1 1 modulo square. So again, half. So if you have the state 1 and you measure it in the x basis, then you get the state outcome plus with probability half minus with probability half. On the other hand, now the point is that suppose your algorithm or your protocol, whatever, requires you to measure in x basis, and the quantum computer is not allowing you to do so because every measurement in the quantum computer is in z basis. So what can you do? You can always apply a good rotation that will help you to do the Z measurement only, but equipped with that particular quantum gate, this entire box, this entire red dotted box with the Hadamard gate and the Z measurement is equivalent to X measurement. So let's see. So what happens? We have this X gate, it is giving 1. We had this 1, but now we have applied the Hadamard gate. So the Hadamard gate on 1 gives this particular state. So what is this probability? We again take half out. It is modulo 0 0 minus 0 1 square half. We take half out. It is 1 0 minus 1 1 square half. So we have the same outcome. So even though your quantum computer does not allow you to measure in any other basis than Z basis, if you need to really measure it in some other basis, then you can always find out a proper gate. For this particular example, Hadamard was the proper gate. But if you want to measure in some other basis, for example, if you want to measure in something called a Y basis, you will require what is called an S gate followed by a Hadamard gate and things like this. So you need to find out what that extra rotation gate is such that these two measurements become equivalent. So it's not a problem that it is Z measurement that is only allowed in a quantum computer. So Deboshnita, any questions here? Else we will
Yes,
move.
so Shubhranil is asking what is a basis, and and someone else I can't remember the name, but if you could please go to the previous slide and the circuit and explain what is basically the X operator and what is X measurement. They are getting confused between
Yeah.
this.
Yes, I understand. That is exactly understandable. So, what is a basis? A basis is that if you have a vector space. So, see, suppose, so let's say, let's draw here. We have a vector space. So, we have all been drawing graphs like this, right? This is the x-axis and this is the y-axis. Any point that you plot on here can be written as something of x plus something of y. So this portion of x, this portion of y. So a basis is the minimum number of vectors that you need to take so that you can span the entire vector space, or in other words, any vector you take in that vector space, for example, this point, this point, this point, any point that you take, you can always represent it using these vectors. So that is called a basis. So here we have been dealing with x and y throughout our life. Instead, what I have written this as 0 and this as 1, nothing else. And the next question, that is obviously a very valid question. What is X operator and what is X measurement? So again, remember, X operator is evolving the state. So we have the quantum state 0. If we have the X operator on this becomes 1. But when we measure this state in a particular basis, in the X basis, so X basis has the eigenvectors. These are the eigenvectors plus and minus. So whenever you measure with X, so if I say measure X, that means that you are going to get the outcome plus and minus irrespective of what your circuit is. So this green box X is an operator, it is evolving the state, and you can think of this black meter box written X as another operator which is some way collapsing the state. So whatever your state be, it is collapsing it to either plus or minus with this probability governed by Bopon rule. So yes, this is, so hopefully this actually helps you, that this is evolving the state and this is collapsing the state. So measurement is collapse and gate is evolve. Okay, so we have two small things just to discuss, and I don't have a lot of time also. So composite quantum systems. So what happens if we have more than one qubits? We have all been talking about one qubit. We have seen how to evolve it. We have seen how to measure it. But what happens if we have more than one qubits? So suppose we have these two qubits. The first qubit is in the state 0. The second qubit is in the state 1. Now the point is that whenever you have a composite system, this is a postulate that you get a tensor product of these two. So what is the tensor product of 0 and 1? So remember, 0 is 1, 0, 1 is 0, 1. So tensor product basically means the first qubit, it is 1 times the entire of the second, the first entry, 1 times entire of the second matrix, and the second entry 0 again times entire of the second matrix. This is the definition of tensor product. So what you get is 0, 1, 0, 0. So these two qubits, 0 tensor 1, gives you this type of matrix representation. You can again verify that this is a normalized matrix. That is, if you take its inner product with itself, it will be 1. So yeah. Now, as you can see that initially, what was the dimension of this particular thing? The dimension was 2. What is the dimension of this? 4. You can try out that if you take 3 qubits, the dimension will be 8, 2 cube. So remember the analogy of coin that I was saying, that if you have 3 coins on the edge, you can do 8 works at the same time. So if you have 3 qubits, your dimension is 8. So if you have n qubits, your dimension is 2 to the power n. So it's a huge search space compared to classical system. And after COVID, all of you understand how bad or how good, depending on the context, exponential can be. So it's a huge search space. Henceforth, whenever we have this composite system, we will just ignore this tensor product and we will write it as 0, 1, or even like this. But it always implies that there is a tensor product. Now, what happens if we measure the composite system? So suppose here is a system. It's a 2-qubit system and it's in a superposition state. What happens if we measure the state 0, 0? So remember, when we are measuring alpha 0 plus beta 1, the probability of getting 0 was mod alpha square. So it is the modulo of the coefficient whole square. So it is modulo this whole square. So that will be 3 times 8. This is also 3 times 8 because they are the same. This is 1 over 2 root 2 square. So that is 1 over 8. And this is 1 over the 8. And you could check that the probability is sum of 1. But this is a 2-qubit state. I may want to measure only the first qubit. So what happens there? I need to write it down. So remember, I have written it down in a broken form, but as I said, that it is a tensor product of 2 qubits. So how can I write this? So let's write it down like this. Psi is root 3 over 2, 0 for the first qubit taking out, times 1 over root 2, 0 minus 1 over root 2, 1 plus 1 half 1, 1 over root 2, 0 minus 1 over root 2, 1. So this is just factorization. Root 3 over 2, 0 plus half 1 tensor 1 over root 2, 0 minus 1 over root 2, 1. So we have both of our qubits. And if we measure only the first qubit, then probability of getting 0 becomes square of the amplitude, so it is 3/4, and probability of getting 1 is 1/4. The second qubit remains unchanged. It remains as it is. That is exactly what should happen, right? If there are two qubits, one is with one of you and one is with me, if I measure my qubit, then my qubit will collapse, not yours. So that is what we get here, how you can find out the probability if you measure a single qubit. You can do the same exercise on the second qubit as well. The first qubit will remain unchanged. Is it always so? So here is a thing. So here is one more example where you can very easily factorize. But what happens if you have a state like this, the red colored state? Can you factorize? Well, it seems you can't, but maybe you can, just it's not very obvious by looking into it. So let's suppose that you can, and the first qubit will have the form A0 plus B1, and the second qubit will have the form C0 plus D1. We need to just find out what ABCD is. So we have AC00 plus BC10 plus AD01 plus BD11. Now from this equation, what we have, AC is equal to 1 over root 2, BD is equal to 1 over root 2. Now BC is equal to 0, AD is equal to 0. So we have four unknown, four equations. We just need to solve it. But let's focus on this part only. BC is equal to 0. When can BC be 0? Then either B is equal to 0 or C is equal to 0 or both of them are 0. Now, if B is equal to 0, if B is equal to 0, that means BD is equal to 0. But we have already said that BD should be 1 over square root 2. So maybe C is equal to 0, B is not. But if C is equal to 0, that means AC is equal to 0. But we have already said that AC should be 1 over root 2. So yes, we cannot factorize a state here, but we have a valid 2-qubit state of this form, which we cannot factorize and write as a tensor product of the two states. And such a state is called entangled. So what this means? Well, it's just entangled. How? We don't know, but it's entangled. There are two qubits, but you cannot express it mathematically in the form of both the qubits. So I read somewhere a very nice analogy that you can say that, suppose you have a car, you can say you know everything about the car, but don't ask me about maybe its tire, its steering. I can't say about the individual things. I know the entire thing. So here you know the entire thing. But if I ask you what is the first qubit, well, don't ask me that. I am not very comfortable with that question. That is entanglement. So the next, so here is Bell state. This you will see next tomorrow in more detail. That this is what we saw. This was the 5 plus was the state we saw, and you can have four such states. These are called Bell states, and they are orthogonal to each other. They form a basis of the 2-qubit state, and they have use in like so many things. Hopefully, you are going to see super dense coding tomorrow. But this is actually important. What happens when you measure an entangled state? Well, so suppose some of you and I, we too have these two qubits entangled. You are at your home, I am in my home. We don't know where we are actually. And I measure my qubit. So suppose I have the first qubit, you have the second qubit. I measure my qubit. So what is the probability of getting 0? So this is my qubit. What is the probability of getting 0? Modulo square of the amplitude. Half. Fine. What is the probability of getting 1? Also half. Fine. So we saw just before that if we measure the first qubit collapse, nothing happens to the second qubit. But here, if I get the outcome 0, then I cannot have the outcome 1. So this entire thing gets ruled out. So now your qubit is also in state 0. On the other hand, if I get the outcome 1, then I cannot have the outcome 0. So this entire thing is ruled out, and I am left with and you are left with this outcome 1. So think about it, how beautiful, or what should I say, how confusing, how spooky this is, that we are at a distance, we can be like anywhere in the world, anywhere in the universe. We have this entangled qubits. You did nothing to your qubit. I am not communicating with you or anything. I just measure my qubit, your qubit collapsed. And here, this is what Einstein termed as spooky action at a distance. He called entanglement spooky action at a distance because he couldn't really explain what is going on. Till today, as far as I know, there is no valid or concrete explanation what is going on. There are many theories, but like what exactly is going on, we don't know. Something is going on. Yeah. But entanglement is like at the heart of quantum computing. Just as superposition is something that has no classical analog, entanglement is also something that has no classical analog. And these two are at the heart of quantum computing. So just last one thing, and I'll hand over to Debosmita. I'm taking some of her time actually, is the no cloning theorem. This is actually very important. Is that what is cloning? So it is, think of like a Xerox machine. You go and give your copy and you will get another copy. So suppose your qubit is shy and you have B, which is a blank state. It can be any state. You just give a blank paper and you get two copies of shy. So that's basically cloning or Xerox. So what do I mean when I ask that does there exist a universal cloning machine C? So just as when you have a Xerox machine, you don't require different buttons for, if you are giving a Bengali copy, you have a different button. If you are giving an English copy, you have a different button. No, whatever you give, you just press the Xerox button and the blank paper will make a copy of it. So that is what we mean by a universal cloner. It does not depend on the input state. So let's assume there is one such state, and there is one such cloner. This C is that operator. So C acting on 0 and a blank state gives two copies of 0, and 1 on blank state gives two copies of 1. So what we expect, so expect is that when C acts on this, it will give you alpha 0 plus beta 1, two copies of alpha 0 plus beta 1. But let's see what happens in reality. So here we have C alpha 0 B plus beta 1 B. So we can take alpha out, C 0 B plus beta out, C 1 B. We already know what is C0B. C0B is 0 0 and C1B is 1 1. This is not equal to alpha 0 plus beta 1 twice. You can understand because there are like no 0 1 1 0 terms. So what this means is that there is no universal cloner on which you can actually apply it on any state and it will make a clone of that state. It will copy that state. And this has a lot of implications in quantum computing. The first implication you can think of, we won't go into that in this fall fest, but is quantum cryptography. If I am sending a quantum state, a hacker cannot just take that quantum state and make a copy of it. That's not allowed. Or so this is a good thing. And maybe a bad thing is that in classical circuits, we have what is called as fan out. So suppose you are doing a gate here, and then you give the inputs to two other gates. This is allowed classically. But this particular thing is not allowed in quantum because this is cloning. So you cannot have such systems here. Your quantum system cannot do copy paste, control C, control V, not allowed in a quantum computer. So yes, that's all I wanted to talk about. And if there are any questions, like one
Yes.
maybe, and then I can, yeah.
So there is one confusion from few of the students that the measuring a qubit in entangled state, the previous slide.
Okay. So here, so
Yes.
try to see, yes. Okay. Try to see what happens. You have this state 1 over root 2 0 0 plus 1 over root 2 1 1. Okay, let's write it like this. It will be better. 1 over root 2 0a 0b plus 1 over root 2 1a 1b. I am A and I am going to measure my qubit. B can be anywhere. Now remember, just to go back and try to recall, when we had this state 1 over root 2 0 plus 1, we said that we get the outcome 0 with probability half. So that means once we measure, the state is 0 with probability half, the state is 1 with probability half, the state has collapsed. The superposition no longer exists. The state is either 0 or the state is 1. So here, if we do the same thing, if I measure my first qubit, I will get, so what is the probability of getting, I am just measuring 0, A, so qubit A. So think of qubit A. So what will happen? I will get 0 with probability half. I will get 1 with probability half. Why so? Because it's basically modulo of the coefficient square, that is half. Good. Now let's assume that I have got the outcome 0 of my first qubit. So now the state has collapsed and there cannot be any 1A portion. So once I have measured and I have got this outcome 0A, there cannot be any 1A portion. But if there is no 1A portion, what happens to this portion? This portion does not exist. This portion cannot exist because my measurement rule is saying that once I measure and I get this outcome 0A, I cannot have the outcome 1A because the system has collapsed. But now this is a property of entanglement, is that the system has collapsed, but taking the other system also with it. That is why it is entangled. And yes, the uneasiness that it seems, that is what quantum computing or quantum mechanics, that is what entanglement is all about. That uneasiness, that yeah, I mean, the maths works out, but it doesn't seem right. So it didn't even seem right to Einstein. That's why he called it a spooky action at a distance. It doesn't seem right, but that's what happens. That if there cannot be no, if there can be no trace of 1A, then this entire state must collapse. And although the system B has not been operated on, it has not been measured, it has not evolved, but even then the outcome is 0A, 0B. So I have changed the system B as well. So yeah, that's entanglement actually. So maybe what we can do, that if there are more questions, we can take it on Discord and we can leave it to Devoshmita now.
Thank you so much, Ritajit, for this wonderful session. And now, basically, I am making Ritajit the host, and then you can continue with it.